So our next speaker is going to tell us something about the long relationship that we've had with Cray, and I'd like to introduce Jeff Brooks, who is the Cray Director of Project Management. Here you go, Jeff.
Thanks very much. Yeah, so I got asked to come out here. Pete Ungaro couldn't make it, unfortunately, because we're having a big leadership meeting in Phoenix. And I was there too, but they said, you go. And so I've not been here for the 40 years, but I have been working at Cray for 26 or 7, something like that. So when I think about NERSC and Cray, and you sort of think, when did it all begin? And a lot of people might say 1978 because that's when the Cray 1 arrived here. And but of course everybody knows that you might say we were here from the very beginning because the CDC 6600. I mean, everybody knows that's a Seymour Cray machine. Everybody knows that he moved to Chippewa Falls in 1962 because he had to get away from the executives in Minneapolis that were troublesome. And a lot of the guys went with him to Cray Research when it was started in 1972. But I claim that our relationship, Cray's relationship with NERSC, actually goes back to 10 years before NERSC even started. And the reason for that is, you all know you started with a 6600, but that was actually serial 1. So a lot of times people talk about the 6600 being the first supercomputer ever. So NERSC actually started with the first supercomputer that was ever built. Now, it was hand-me-downs from Livermore. They'd used it for 10 years, and it was pretty tired out by the time you got it, but it was serial 1. In a lot of ways, this was, I never worked on one of these. Now, there's one of these in the Chippewa Museum, and apparently Paul Allen's trying to get it running again. So that'd be kind of cool if that happens. But a lot of times people call this the first RISC computer. It had a load store architecture. It had, I think, only 70-some operands. And, Patterson would coin this term years and years later, but the properties were in this machine. And so, of course, the joke at Cray was always, it stands for really invented by Seymour Cray. I wonder whose job it was to answer those 4 acoustic modems, manually when users called in to use this thing. Of course, that machine was also the subject of this famous memo, which has now been 50 years, from T.J. Watson, kind of an angry memo about, and it's the beginning of the rivalry that we've had with IBM, where he talks about this small lab in Chippewa and, just a handful of people, including the janitor, and how can we lose with our vast development efforts? Now, there's supposedly this legend at Cray, I don't know if it's true, that Seymour saw this memo and said, the answer to his question is right in his own memo, but I don't know if that's really true or not. So, of course, you guys know what came after that was the CDC 7600. I think the major new feature that was important in this thing was pipeline functional units. It was the first machine with pipeline functional units. You would issue a multiply. It takes 10 clocks to go through the multiply, and on the 6600, you'd have to wait 10 clocks to issue another multiply. But on this machine, oh no, you could just issue a multiply right after, as soon as you went down the pipeline. Of course, this became very important for vector stuff that would happen later on. And this, a lot of people at Cray that are still there are a few people left that actually worked on this machine. And of course, this was Freon cooled. In fact, the Paul Allen thing, what I've heard is the hardest thing to get that old machine running again is to get the Freon refrigerant stuff going in the thing. Of course, and then there's the Cray 1. I actually worked on one of these at the University of Minnesota. It's the first Cray I ever got on, but it was serial 12, not serial 6. And, you ran the CTSS operating system on here, which is probably the first time you weren't happy with what the vendor gave you and decided to do something else instead. So another one, you've seen the pictures. These disk drives always reminded me of the laundromat, but we had DD29s at Minnesota. These were 19s. And we had the same tricks where we could do stuff with I/O and make them walk down the floor and so on. It was kind of neat stuff. But the big innovations in this, I think, really were vector processing, of course, but also compilers. We had a guy named Dick Nelson, a really smart guy. He invented dependency analysis in a compiler. He wrote the first compiler, and he wrote it in assembler. It was like later on, the compilers were written in Pascal of all goofy languages. But back in those days, the compiler was written in assembler. It was lightning fast, CFT, and then later CFT2. Packaging was pretty cool with the Freon. First one to use integrated circuits, and of course, vector processing. Now, I'm going to talk about transitions. I think one of the things that NERSC is pretty good at is transitioning users from one technology to the next. So this is the first major transition, right? You went from a scalar machine to a vector machine. But I claim this was the easiest transition. And the reason was, in the marketplace, all you had to do was take a Fortran code and you run it on this machine and it would be faster than anything in the world, doing nothing. And then, of course, what you try to do is you try to use this vector processing and so on and get another order of magnitude. So I think this was probably a pretty easy transition from the 7600. And then, of course, after this is the XMP, which came in 1984, shown in the foreground of this picture. Of course, Steve Chen did this machine because Seymour was off doing the Cray 2 at this point in time. And as a benchmarker, this is kind of when I was starting at Cray, we were still selling these things. And this was a great machine. It had the multi-port memory you could do 2 reads in a store. It had this cool new instruction called gather scatter. No one had ever had that before. We have a register full of operands and you can gather out of it. And then it had this feature called chaining, where you could go right out of a vector register right into a functional unit. You didn't have to wait for the whole register to be filled. These were really pretty cool features that really made this a pretty good machine. And I think that's why Cray sold so many of these things. I always loved this machine because this was just such a great looking machine. One of these is in some art museum in France somewhere, because these are so attractive, the old Cray 2s. I mean, they, world's most expensive aquarium. These were $20 million, and we were enamored with them because they had such this high clock rate. But there were a few innovations in the area. I think the major innovations, the floor inert thing. You remember the early Cray 2s? They had round tanks for that. The reason they had to switch to this design was because the weight of the floor inert was so heavy, it actually warped those plastic cylinders, and they were starting to kind of look like they might crack. That stuff was $200 a gallon, if I remember right. So they went to this design. This is the 8 processor. It was the only one in the world that was delivered here. The other thing on this machine is a benchmarker. It only had a single port memory, so you could read from this memory out into one vector register, but it was hard to go faster than that. You had to use this local memory. There was this local memory. And the compiler was supposed to figure out how to use it. Never did. But if you wanted to do something like matrix multiply, you could squirrel away your temporaries in the local memory. It was the same thing on the XMP that you would do with the B and T registers. I think we'll see that feature come into processors here again. So that will come back. And then we had this macro tasking and micro tasking. So we're starting to use multiple processors. Now, I kind of doubt this was really used too much by users because it didn't really improve the throughput of the machine. These multi-processor machines, it was just really would just run more jobs or more capacity, as Bill put it earlier. But when we had these things dedicated in the lab, we would go and try to do this stuff. And I remember the thrill of getting something to run at a gigaflop on this. If you used all 4 processors and you were doing something that involved a lot of matrix multiply. It's funny how things really haven't changed in all these years. So then came the C90, and this was 1992. And we put a YMP8 in, and the C90 is kind of a terrible name. It was the Cray for the 90s, I guess, but it was called the YMP C90 originally. That was the code name, and then we were, I think, too lazy to change the name. But this was the first one that didn't go to a 3-letter agency that, and I think this is probably the 5th one that went out that came to NERSC. And I think this was the last big flagship vector system that came here before the transition to massively parallel computing. Now this machine, I looked up the top 500 in 1993. It was the first year. And on that list, it was number 19. And I'm saying here it could have been number 6. So I'll tell you the story behind that. You run LINPACK on this thing. It's a lot of matrix multiply. And in the benchmark lab at Cray, we'd figured out how to do this goofy thing called Strawson's matrix multiply. And we coded up a version of LINPACK on this machine. It actually ran at 21 gigaflops. Well, the machine only has a peak of 16. And we submitted that to Jack Dongarra, and he wrote back and he said, "That's impossible." And I said, "How'd you do it?" So we told him how we did it. And he says, "Oh, we're not going to allow that." And it was really disappointing because we wanted to pass all those NEC SX, probably SX4s is what they were. So and another funny story about this machine was that it actually had errors in the floating point units. And the first 4 machines that went out had a bug in the floating point unit. You know how terrifying that is? Is it for a vendor when you put out $100 million worth of stuff and there's an error in it? But luckily for us, there's a guy in my group named Dennis Kuba who discovered it doing something with an FFT, And he got on this machine. He said, "There's a bug in this." And sure enough, is there a software workaround? No. But fortunately, at the time, we had an integrated circuit fab. We made our own chips for this thing, believe it or not. And that is this building here. And I'll tell you one thing I never understood. That's a railroad track there. Why'd you put a fab next to a railroad? I mean, even today, our development building is up at the top. A train goes by, the building shakes, you know. I can't imagine that was a good idea. But literally, we got that chip respun and back in a machine in 1 week. You know, today this takes months, you know, to do this. So it was kind of nice having a fab. So meanwhile, in the marketplace, this new style of computing was coming out and emerging. And I mean, we kind of think there were a lot of snake oil salesmen out here at this point in time. You know, they were kind of, oh, this is great. Remember, and there were all these phony claims about how great these machines were and massively parallel machines and so on. And this is about the era when David Bailey wrote this funny paper about the 12 ways to fool the masses when you're showing results on massively parallel supercomputers. I mean, this was always a really funny paper. I really enjoyed it. And I think you could write it today now, except now it's GPU computing or something else. I mean, there was a lot of buzz about massively parallel computing, and you know, Eugene Brooks, Attack of the Killer Micros, all that was going on. We decided, yeah, there was something to this, and we better get on the ball here. So Steve Nelson kicked off this T3D project inside Cray, and one of the test beds came here. So this grew out of this thing that Steve Nelson put together called the MPP Advisory Group. This is our way to try to get intimate with customers. What do you want? Let's try to build this thing. And believe it or not, from the time that project started, we delivered a machine in 18 months later. It is handy to have a fab right next door. So this was all kind of made out of YMP-like technology, and we could build the chips and respin them right next door. So this was an old 150 megahertz EV4, and it had a YMP front end. And so I claim this was the first ES login, you know, because the YMP had the mature Unicos operating system. This had some goofy microkernel, and I can't remember if it was Chorus or Mach. I forget which one came first. But we certainly didn't want to run the user's compiles on all that. So some of the cool stuff in this machine, Alice mentioned writing a book about this. I think I might have contributed to some, did I help you with that? Oh, okay. There was this one-sided get put thing. When this thing was brand new, there was no message passing. There was this PVM thing from Al Geist, and there was nothing. But Bob Numrich wrote this get and a put. You know, you just kind of, and that's all we had when we started. But it was really low latency. I think it was 1 or 2 microseconds. So if you think about it, it's no better today than it was back then. So this was pretty cool. 3D Torus, it was pretty high density. You could get up to 512 processing elements in one of these cabinets that use the same kind of cooling as the YMP. There, you know, not all our projects work out well. We had this parallel programming language called Craft, and Cray Research Adaptive Fortran Translator or something like that. And it was not great. And go back to the 12 ways to fool the masses. I remember going to a conference in Edinburgh. They had one of these. Someone showed this great graph scaling all the way to 512. I'm using Craft. But Craft didn't let the data cache work. You had to turn the cache off for this thing to work. So you asked him, it's a great scaling curve, but where are you at the first processor? Oh, well, it's like 1 megaflop or something like that. So, and then PVM was sort of coming on here, and that's what we ended up, you know, taking into the T3E. Now, this wasn't exactly SSP, you know. I think SSP is a great idea, and it's a great thing that NERSC has done. But it was the closest thing at the time. And there was another young, good-looking guy named Horst Simon who was at NASA Ames and producing this thing called the NAS Parallel Benchmarks. And it was really this effort to kind of have an honest-to-goodness comparison between different architectures and machines running these algorithms that were important to NASA Ames. And we implemented these things inside Cray. In fact, on the T3D, we implemented all 8 benchmarks using these 2 calls. Call get, call barrier. And you can do them all with this because there was no other software that worked. And actually turned out this is pretty easy. And this Bob Numrich, as I mentioned, came up with this idea. It went on to become the SHMEM programming model, which is still around today. And he followed up this whole idea with something called F-, which eventually became Col-Ray Fortran. So I actually dug up this paper from 1993 that Horst had done. We must have drove Horst nuts because we would send him new results like every week. Every time we made something go a little bit faster, or we had a new compiler, we'd go run them again, Charles Grassel and myself. But the way he did the measurements was how many YMP units of performance, sort of like that's the gold standard, a YMP single processor. And you could see on an 8 processor YMP, we could get almost a speed up of 7. That isn't going to work in an MPP world, is it? And down here in the T3D, you could see that with 128, we could surpass a YMP 8, right? And there weren't a lot of MPPs that could do that. So there we are at 64 processors. So there was a 128 processor one here, I think, that was here early. And there was another fellow I used to look at his papers. This guy named Harvey Wasserman. And I tell you, this paper, Harvey, that you wrote about the RS6000, this got our attention in Cray. It really did. We looked at this, and this leadership we had, I mean, you think back to the old Crays, you just compile a code, you're faster than anyone in the world. All of a sudden, this was getting eroded. Now it was you just compile the code, and if it's got long vectors like Pueblo or Newt or whatever those codes were, then you were good. But all these other ones, these microprocessors were starting to look pretty good. In particular, this 590 workstation really caught our attention. It shook us up in Cray. We said, we got to do this new direction. Now, part of it was, these vector machines were expensive. And so one thing that we tried to do was to make them cheaper. And I noticed looking through, we sold 200 or 300 or 400 of these J90s. They went all. I think there's J90s still running. There's probably one at Nurse somewhere still running DMF back in a closet. Basically, it was a way to leverage all the software on the expensive vector machines and kind of put it in a CMOS package instead of an ECL package. And these were good machines, and you had a few of these. You had J9, and I think part of this, another thing I saw as I looked through the history, you have a pretty good track record of keeping continuous service to the users. So when it was time to move the C90 to Berkeley, you kind of put users on this for a while you were doing the move. And this is probably the last systems at NERSC that used the Cray floating point format. Remember that? That was a little different than the IEEE. It had a bigger mantissa, bigger exponent and a smaller mantissa, I think. We used to get beat up all the time by some torture test on the floating point stuff. Later on, the SV1 had IEEE in it. So this is probably one of my favorite machines to ever work on, the T3E. And you guys got the 128 processor system in 1996. Bill's talked about kind of making this a production supercomputer, and I really couldn't agree more, and it really wasn't a production supercomputer when we were starting out. So I've got a couple things I thought I'd share with you. We'll start with this bullet called the R5 debacle. Well, R5 is a router chip. So we had, how many chips were in here? There was a C chip, I chip, M chip, R chip. We had 4 or 5 custom chips. And we weren't making them next door at the fab. 1 or 2 of them we were, but the other ones we were sending out to LSI. So the router 4 chip, the 4th spin, it's got some problems. We know exactly what the problems are. The logic designers figure this out. They say, oh, here it is. They fix the Verilog or whatever, send it back to LSI, and 2 or 3 weeks later, it's not overnight now, it's 2 or 3 weeks, chip comes back, they put it in blades, they get it into the system, they boot it all up, kind of looking at this is exactly the way it was before. And say, this is impossible. We changed the logic, we did this, we did that, the other thing. And they could not figure it out until someone got the idea of, let's look at that tape we sent them. And we realized we just respun the R4 chip. So anyway, I think it's been long enough where we can let people know that we did that. It turned out not to be the long pole in the tent of the schedule. And then the other story here you can see is about 2 Bills and 4 Steves. Well, the Bills, as you might guess, are Bill McCurdy and Bill Kramer. And the Steves are all Cray people. And this had to do with a factory test demo in Chippewa Falls in August of 1996. So our sales guy was Al Geller at the time. The 2 Bills were coming to do factory, Lynn was probably there, were coming to do a factory trial, and they wanted to run a bunch of applications on 128 processors. Well, we'd gone from 32 to a 64, everything worked, and then we went up to 128, and nothing worked. Absolutely nothing. None of the NERSC applications even started. And this was going on for almost a week and a half, 2 weeks. And no one could figure it out. We didn't have debuggers on this thing. I mean, people were trying to figure this out. And I think you guys landed in Minneapolis. You were probably in the car on the way over, and Steve Piatz realized there's this constant that times out. And as we doubled the size of the machine, the time to launch the job just exceeded the constant. He figured it out with print statements. All he did was change the constant, and everything just worked. So you guys showed up, and you didn't know that we were terrified. We were about to be raked over the coals. Everything went perfectly, and you actually thought that we knew what we were doing. From a benchmarker's perspective, I think some of the neat stuff in here were e-registers, which was a Steve Scott idea. Stream buffers, which was an idea from Rick Kessler. Instead of a third-level cache, we had these smart buffers that would read ahead, and there were 6 of them. So if you had 6 right-hand sides, this thing worked really well. The whole OS, the whole Unicos MK architecture, Unicos ran on the login nodes, and then this microkernel ran everywhere else. That's sort of the same idea we're doing today on Edison. Colray Fortran, checkpoint restart, PVM, eventually MPI, and we got quite a bit of help from the Edinburgh folks to make the MPI good, use the message queues and do all that. But this is the big transition, of course, to go from one memory to lots of memories, and I think you did a good job. And I remember this guy too, and I'm glad that he showed up, because this was our proudest achievement on this machine, was to run the first code at a teraflop. And I know there were guys in here from Pittsburgh and other places, but you look exactly the same. I mean, it's... So this was all going swimmingly well at Cray. We were pretty excited. We thought we were going to make this transition, of course, and then this happened. And we had these 2 machines. Now, SGI bought us, and that was okay, but we had these 2 machines, This one was the distributed memory. This one, they wanted to push the shared memory, the Origin 2000. As you can imagine, whoever gets bought is the one that has to kind of follow the orders. And over time, it was kind of sad. That one kind of dropped out of the picture, and all the focus went into this line. And I thought that was kind of a shame, because I thought making the leap to distributed computing, this is almost like going backwards. But that was what we ended up doing. So there was a T3F development project that was canceled, and that was a bit upsetting. And we did our best with this to try to sell as many as possible. This is what ended up going into NASA Ames, big systems built out of this. But I don't think it ever quite worked out as well. And of course, you didn't buy a Cray the next time. This wasn't a Cray, but you turned out you bought it from a Cray guy. He just didn't know he was a Cray guy at the time. So honestly, when I talked to Pete, he says, boy, I can remember going there when he was trying to sell probably SP1, and he said, it's like a Cray museum there. Just the beautiful machines, and he's coming in with these black boxes. So kind of in this transition, I kind of left the benchmarking group, and I went into product management. And so I started to help try to sell these machines, and I got a little bit excited with the Redstorm thing, and actually took a brief time away from Cray and came back. And I was pretty excited when we got the call it was either from Lynn Rippey or from Bill that, hey, we want, come in and talk to us. And there was some room here in this building where we had to spend weeks. And it reminded me of being inside a submarine. It was this gray room, and there were pipes coming through, and they didn't let us out until... so it was the first negotiation for this, but there were a number of things that we had to do to the machine to make it usable at NERSC. One of them had to do with connecting into this NERSC global file system. So you guys kind of got us developing this DVS technology so that we could mount GPFS on this system. And this was a fragile system. There were issues with it. You like to design a system without a single point of failure, and this thing had thousands of single points of failure, because if you lost a single lane on the C-star, the thing would come down. So it was very sensitive and so on. I heard a rumor, I don't know if this is true, that Nick Cardo had some rubber chicken he kept in the machine that had something to do with voodoo or luck or something. But I think he was blocking the airflow, and that's what caused those...
No, the chicken was required.
So we did an upgrade in place here on this machine from a dual core to quad core, and Dan Unger came up with this method of how we could do it. And again, back to this, we tried to keep service open the whole time. And so we would take down every other column or something like that and keep the remaining stuff away. You know, you guys had orchestrated a pretty good plan to do this. And I think that was a worthwhile upgrade. You know, and I know there was other pain with this machine, with the memory and so on, but I hope over its life it delivered some good science. The other thing I wanted to mention is Bill made the decision not to go to Catamount on this machine. Catamount was what we had, the mature operating system. We were transitioning to Linux, but we weren't ready to do it on 102 cabinets. But you guys pushed us to get it going, and I think that piece of it worked out okay in the end.
Are you willing to thank me for that now?
Yes. So it's not going. And of course, it really wasn't 102 cabinets. Everybody knows that it was really 108 because of that darn pole in the middle of the computer room, and we had to put in that column of empty cabinets and put them up on those earthquake deals around and so on. So this ran. Now, Franklin lives on. We took these cabinets back, and they've been remanufactured, and they've gone out as XE6 Nanos. They've gone out as Eureka systems. So Franklin was an organ donor at the end of its life. Did not go into a landfill. Now, I know you're thinking, how do you come up with these great names, you know, now that you're in product management, Jeff? You know, what we were going to call that thing when we productized Redstorm, we were going to call it Cray RS, believe it or not. And then we found out from the Australians that RS in Australia means the same thing as BS does here, except with a rat instead of a bull. So we thought maybe this is not such a good name. So next door to me was William White, who was the product manager for the T3E, and he had these plastic injection mold letters on his door when we were trying to do this alpha cluster. And it said Cray T3X. I said, well, those are nice letters. Let's just check. There you go. That'll do. And that was how that came about. So then, you know, things started to get better, right? We did the Gemini interconnect, and Gemini was just way, way better than C-Star. And I was among the people that made the decision to put the Gemini chip into the Taurus infrastructure instead of the Hypercube infrastructure, which is where it was supposed to go. So that has the good and the bad. I think if it was Hypercube, we probably couldn't have built Blue Waters. And I don't think we could have done the upgrades in place that we did at Oak Ridge. But the downside is when you start to make big Tauruses, you have to start to care about placement and everything, as you've sort of discovered. But now all of a sudden, boy, we're getting to 24 core nodes. We get this warm swap thing working. We get better MPI latency, and this is just way less fragile than the XT4 was. And we have cool murals now. That was kind of neat. You know where that came from was there was a customer down in Erdek. They wanted us to spray camouflage on the machine. So we, you know, Chippewa Falls, there's guys that spray paint camo all the time. We took the doors down and sprayed them. And, then a guy in manufacturing said, we could do inserts and then they could put whatever they want on there. And we always like this idea because it's sort of like saying, this is one machine. It's not a bunch of individual nodes. This is not a cluster. This is one MPP supercomputer. And that's kind of what you know, I'm glad you guys do a great job with the pictures you put on here. One more naming thing. How do, you know, they come up with these goofy names? EcoFlex. Eco, because of course you got to be green, you know, even though it's got a bunch of refrigerant and stuff, probably isn't so good. Phase, liquid, exchange. It's pretty good, huh? We just made that up. This fellow in the storage group, Tom Sherman, he says, that is the dumbest name I've ever heard. It sounds like phlegm or spitting or something. And I said, this coming from the guy who named Synexion. I mean, so I'll tell you why I'm at it. You know, this was our #1 rejected marketing slogan for the XE6. Is, you know it's powerful by its mighty roar. It was actually a loud machine, you know, and I see in the health and safety thing in the bathroom that, you know, wear earplugs around this. It's not as bad. I can tell you with the Cray, we're at the 100th anniversary of mustard gas, you know, and with the Cray 2, you take a burn in there, it makes mustard gas, so that's a little more serious. And then finally, Edison. That's what, we're excited to have this machine here, and it is the first XC30 that's gone out to a customer site. And again, there's an interim plan, right? We came out with a small machine. I think you guys did the right stuff. You got the storage in, you got everything tested, and then we grew the compute partition. So it was a pleasure to work with the procurement team on this one, even though it was different from you guys change every time. There's new people in these procurement things, except for Lynn. She's always there. So, I mean, this was an x86 machine again, but it was different. Gemini went to Aries, AMD went to Intel, Copper went to optics, Vertical went to horizontal. So we used to go vertical cooling, now we're doing horizontal cooling. and loud went to quiet, thankfully. And we did our best at Cray to make this a smooth transition for the users and administrators. And we tried to do that by using the same OS, by using the same compilers. I know that we didn't have PGI on there. We do have it now if you do need it, but we did our best to make it a smooth transition. And I think this has been a good transition from what I see. You know, there's the machine when it was, it's a used machine. Did you know that? Yeah. It was the DARPA demo machine, and this was September of 12. And this demo went off without a hitch. I mean, everything with the Aries was good, and we took the skins off and changed the doors, and then that became your first 4 cabinets. And then we delivered that and announced it at Supercomputing, and we have a bunch of orders. I don't know how many petaflop scale systems we have, but we just had a record year with 25% revenue growth. It's all this stuff. And at Supercomputing, I like to, you know, when I look at the big scale stuff at NERSC, I like to go to your webpage. And this time I went on September 4th, and I like to look at the kind of stuff that's happening on these big machines and show that, you know, it used to be a big deal that we would scale to 100 processors, that you can go to thousands, hundreds of thousands. So I think that's pretty neat stuff. So it's been a great 40 years. Our slogan, you know, it used to be world's fastest computers. We made it a little more, I don't know, complicated. We build computational tools that help change the world. And you notice help is really, you know, at the end of the day, we just make a tool. It's just a thing, you know, and it doesn't really do anything until it gets in the hand of a center. There's user services folks. There's a bunch of users doing really smart stuff. And we know that it's our customers who do the real heavy lifting and actually do that change the world stuff. But it's just a pleasure to have been part of it for 40 years. So thanks for a great 40 years. And on behalf of Cray, I hope we have a good relationship for the next 40. So thanks.